Okay, it's time to start. This is Math 1151, and we're going to talk about Section 2.5. I'm Bart Snapp. How was that quiz yesterday? Was it okay? I hope it was good. If it wasn't, you can't worry about it. If it wasn't okay, what you need to do is you need to figure out how to solve that problem, and make sure that if you ever see a similar problem, it won't get you again. Okay? You don't need to beat yourself up, but you just need to not let it happen again. That's what needs to happen. I know it's easier said than done. I beat myself up about stuff, okay? But you just got to be like, who cares? Quiz. Take the next quiz. All right? What questions do you have? When's the next quiz? Next Thursday, and it's going to cover up through section 2.4. That's right. Okay. When are my office hours? Does anybody know the answer to that question? Nobody knows the answer. They're Monday, Wednesday, Friday, 4 to 5. Okay? And you can also visit your TA's office hours. They would love to see you. Oh, all right, I'm serious, actually. So, should we just get started? Yeah, let's do it. Last time, we were talking about limits. We're talking about infinite limits. Infinite limits. And maybe a good example of an infinite limit, you should carry around examples of these things with you, okay? So if somebody says to me, what's an example of an infinite limit, Bart? I could say, well, how about the limit as x goes to 0? And then what do I want to put here? Can somebody help me out? I want to make an example of an infinite limit. Yeah? 1 over x squared. And, I would even, in my head, this guy's smarter than me. In my head, I was thinking 1 over x. And like, oh no, that's not going to work. 1 over x doesn't work because 1 over x looks like this, right? The limit doesn't exist. But if you square it, then, that's going to work. And this is equal to infinity. And the plot looks like, it's going to look like this. So and what's this line called? What's this, where it goes to infinity? What's that thing called? Do you guys remember what that's called? A vertical asymptote. That's exactly right. And if somebody asks you to find all the vertical asymptotes, which is a fair question, all you do is you find all the points where the function approaches infinity, negative infinity, or either one from either side, okay? Where it goes like this. Those are your this one, and those are your choices. All right. Now, there's something that sounds like infinite limits that's a little different. They're called, this is 2.4, by the way, 2.4. And in 2.5, we have limits at infinity. Limits at infinity. These are approaching infinity, and these are at infinity. Yeah. But infinite limits is a good way to say it. So what's a limit at infinity? Well, here's our first example. It'd be the limit as x goes to infinity of 6x minus 9 over x minus 1. So x goes to infinity here. And then we find out what our function does. Now, if this was an infinity, say it's some number, what would you be tempted to do? Plug it in. And infinity, boy, I'm scared to say this on tape. I'm going to say it anyway. It's like a big number, right? Kind of. So if I plug in a big number here and I plug in a big number above, can you really see what's going on? No, it's kind of hard, okay? Maybe if you got your calculator, you might be able to figure it out, but it's a little bit tough. And so what you should do is you look for the highest degree term. You look, here's the idea. I'm going to give you this idea, and hopefully it's completely right, okay? You look for the highest degree term in the numerator or denominator. You look for the highest degree term in the numerator or the denominator. I'm just making this up, so if it's wrong, we're going to find out pretty soon as we work more examples, but I think it's going to be fine. And what is the highest degree term in the numerator or the denominator? We have 6x and we have x, right? Those highest degree term in the numerator is 6x. And so what you do is you take so in our case it's 6x and x for both of those. And what we're going to do is we're going to multiply this by the fraction 1 over x. Be careful with this fraction. Make this bar is bigger. And as long as x is not equal to 0, what does this fraction equal? 1. We're just multiplying by 1. Right? So we multiply by this fraction. So this is equal to the limit as x goes to infinity of, this is going to distribute, right? Distribute this. 6x times 1 over x is 6. Minus 9 over x. And then x times 1 over x is 1. Minus 1 over x. Aha! So we have this now. And what happens to this fraction as x gets large? It goes to 0, right? And so all that's left is 6 over 1, or 6. Kind of makes sense? Yeah. She says, couldn't we just take the first term from the top and the bottom and simplify this fraction? Different texts do it different. I'm following how Briggs does it. When I was actually taught, I was taught a way of looking at for what are called dominant terms. And this is a dominant term, and this is the dominant term here. I would try to follow this way just because I'm trying to do everything by the book. Okay? Yeah. It's all on how much rigor you want inside the course. Yes? Yeah, that's what I'm going to do next, I think. Well, not exact. Yeah, I can do one right now. Okay? Let's do it right now. So she said, can you do an example? These are the dominant terms here, the terms with the highest power of x. Do an example where they're different, right? Here we go. Limit as x goes to infinity of 2x squared minus x plus 3 all over. Oh, well, here's one where they're the same. You want one where they're different. Let's see. Aha. Yes, yes, yes. Oh, let's talk about this one, and then I'll fix that one. Okay. How do I get rid of the x's? What happens to, I'm going to answer your question with a question, okay? What happens to this fraction here as x becomes big? It goes to 0. And so this went to 0. And what happens to this one? As x gets very large, this fraction goes to 0. And so we're just left with 6 minus 0, 1 minus 0. 6 over 1. Is that okay? Yes?
So you said the goal is basically to take the x's out of contention.
He said it very nicely. The goal is to take the x's out of contention, right? You want to get those x's out of there. So let's do this example. We'll move this x out. So it's 2x plus 3 all over 3x squared plus 5. So what's the, what do we multiply by here? We're going to do it the same way. What's the highest degree term of the numerator? It's 2x, and what's the highest degree term of the denominator? 3x squared. And since the 3x squared is the bigger term, we're going to multiply by 1 over x squared, 1 over x squared. So now we distribute, and we're going to get the limit as x goes to infinity of what happens here? 2 over x plus 3 over x squared plus, and then this is going to be 3, right? Plus 5 over x squared. What's going to happen as x becomes very large? These will all go to 0. This is going to equal 0 plus 0 all over 3, which is equal to 0. Is it all right? Yeah. 1 over is whatever is the biggest thing that's going to kill everything when you divide by it. Yeah. He says if you had an absolute value in there, he says what would happen if this was the absolute value of 2x? Same thing. Okay? All right, so now I'm going to show you a different type of example. How about the limit as x goes to infinity of sine of 7x all over x plus 4. What happens here? What do you do here? What do you know about sine of something? It's always between -1 and 1, right? This thing compared to x as x becomes large is basically a constant. Okay, so what's going to happen to this term as x becomes large? It becomes 0. This goes to 0, so this whole thing is equal to 4. The plot looks something like this. It starts off, it's oscillating, and then it just flattens out. Okay? How about we do one more example, and then we try some online examples, see how they look, see if we can do them, and then if we're pretty comfortable, we can move on. Get on to something that's a little bit harder. How about the limit as x goes to infinity of the natural log of x? What happens here? It's kind of tough. If you don't know what these things are, you should plot them. You should say, let's see what happens. And you get your graphing calculator out, and you start to plot natural log of x, and it looks like this. And you start typing some big numbers in. You have your calculator out, right? What you can get you know how to do natural log and everything, right? Right, good. He knows how to do it. What big number should he type into natural log? 100. What's natural log of 100? Natural log of 100 equals 4.6. What's next? 1,000, right? Natural log of 1,000 is equal to 6.9. Natural log of, put in like a million. Yeah. Natural log of a million, 1,000,000. Is that a million? Equals 13.8. This thing grows very slowly, okay? Natural log grows very slowly. What do you think? Does it go to infinity, or does it level off eventually? She says infinity, right? How do you know? How do you know if it goes to infinity? That's the hard part. And why? She says because it doesn't stop growing, and that's true. Why not? How could you argue that it goes to infinity? What's it mean? What's natural log mean? Y equals natural log of x. Let's see. Y equal, let's do natural log of x equals y. Natural log of x equals y. What's that mean if natural log of x equals y? Good. E to the y equals x. And so we want to know if we plug in large enough x, well, can we get as large a value as y as we want? Look at this right here. Can I keep on raising e to the y to numbers? Yeah, absolutely. This is why natural log keeps on growing. Now, it grows incredibly slowly. Okay, so using your calculator here is a little bit complicated, but the limit as x goes to infinity of natural log of x is equal to infinity. And if you want something that grows even slower, natural log of x. Your calculator can't put in a number. I mean, yeah. How would you show this on a test? What you do, okay, he says, how would you show it on a test? On a test, I really think you could just say, unless the question is specifically, explain why natural log of x goes to infinity, you can just write the limit as x goes to infinity of natural log of x is infinity. Okay? But if it says explain it, then you say, well, go back to the definition. And you write this down. And you say, I can plug in as large a value I want for y and get an x out. So natural log is unbounded. That's what you'd say. I don't think they're going to ask you that. You're going to have to know this. But I don't think they're going to ask you to explain why it's true. I could be wrong. I don't write the test. Okay? I probably won't see the test until you take it. And I'll be like, what? All right. Oh yeah, let's do sometimes, by the way, limits at infinity, this is sometimes called end behavior. End behavior. End behavior. So what's the end behavior? Tell me this. What's the limit as x goes to infinity of e to the x? How about the limit as x goes to infinity of e to the minus x? What do these look like? These you just have to know. E to the x, this is e to the x. Right? So what happens as x goes to infinity? It's infinity, right? And e to the minus x looks the same, but it's flipped around, right? So it looks like this. And what's the limit? It's going to be 0. What questions do you have about this? Let's try one of these online exercises to see how hard it is. So here we have the limit as x goes to minus infinity of minus 2. I'll write it down up here, then I'll turn it off in just a second. Limit as x goes to minus infinity of 2x, or is it negative 2x, minus 2x plus 5, all over okay. So how do we do this again? Find the greatest term. What's the greatest term? It's 5x and 2x, but we just worry about the x's. So we multiply by 1 over x times 1 over x, and we're going to get the limit as x goes to minus infinity of, let's see, that's got to be minus 2 plus 5 over x minus 5 plus, minus 10 over x. Is that correct? What happens to these terms as x goes to minus infinity? They go to 0. So this is equal to minus 2 over minus 5. I think that's right. Do you guys think it's right? Let's see what the computer says. Okay, so let's cheat if that's all right with everybody else. I want a hint. You guys know this? You can say hint. First, we multiply the numerator by the reciprocal, the largest power of x, which appears anywhere. That sounds good, right? All right, that sounds good. I'm still not done. So now, yep, that looks exactly like what we have. Oh, they put the limits through there. I don't think you really need to do that, but they added all the steps, okay? Up, minus 2, up 2 over 5, and we can just type in 2 over 5 here and check answer. And yes, we win, okay. And then we can get another question. Can anybody very quickly tell me what the answer to this one is? It's 8 over 7. Let's just do it. All right. 8 over 7. Check answer. Yes! Okay. How about the next one? 6 over 10. Oh, 3. Let's just see what happens. Oh, damn it. 3 over 5. Try again. Your answer is almost correct, but it needs to be simplified. I'll simplify your answer for you. Okay, so this is the sort of thing you can do. You can go onto this Mooculus site and try this out, and they can give you lots and lots of problems to try, and you should be able to do them. Let's just get to the next problem. Let's go to the exercises. You guys have questions about this? What questions? Yes. He says, what would happen? That's what was asked me before, and if they were different powers, if you have two polynomials and the powers are different, there are only two things that can happen. If the power of the numerator is greater than the degree of the numerator is greater than the degree of the denominator, it's going to go to infinity or minus infinity. Okay? It's going to go to one of the infinities. If the degree of the numerator is smaller than the degree of the denominator, then it's going to go to 0. All right? But let me ask you this. I'm writing a test, and I want to know if you guys understand something. And I'm going to ask you a question about a limit as x goes to infinity. What do you think the tempting answer is as x goes to infinity? Infinity is the tempting answer, okay? So my guess is that we're not going to ask you a limit. I mean, we could, okay? But my guess is that I'm guessing we probably wouldn't ask you a limit as x goes to infinity that equals infinity. Unless we're trying to like double bluff you, you know? We're like saying, aha, because they think that it's not going to be infinity, now we're going to make it infinity just to mess with them. Okay, but that's, I'm thinking that's not going to happen. There's one more type of harder problem that we should probably talk about. By the way, how do you study for mathematics? You work problems. You work all the problems you can. Then you work them all again. Okay? You work them till you can work them so fast that you can take the test. Have you ever been in the situation where a math class, the test seems to have way too many questions on it? Yes, that's every math class. Okay? There's going to be a ton of questions on this exam. So you're going to have to work fast. You're going to have to. They're not going to take it easy on you. All right. Limit, well, here's the problem. X squared minus 1 all over x plus 2. Yes? Oh, she says, could you do a sign chart? And so can you explain what you mean by a sign chart here? Mm-hmm. That will work. Yeah. I don't think that's how Briggs does it. So I think that'll be fine. Now, check out this problem here. There's something else. There's another type of asymptote. It's called a slant asymptote. If you plot this, it looks like what do you notice here? It looks like there's a line here, right? Now, what happens as x goes to infinity? What happens to our function as x goes to infinity? It goes to infinity. And this is what we expect because the degree is higher, right? And as x goes to negative infinity, it goes to negative infinity. That's because what's going to happen here is this is going to be very positive and large. This is going to be very negative and not as large. But the negative sign will still send you down to negative infinity. But what we could ask you is, what's the formula for this line? And the way you do this is you use the trick that we used last time in class. Or maybe 2 times. Do you have your hand up? Okay, that's fine. You use long division, polynomial division. So how do we divide? X squared plus 0x minus 1. X plus 2. And so what do I put up here? X. X squared plus 2x, subtract. You get minus 2x minus 1. X minus 2. Minus 2x minus 4. And what happens here? You get a remainder of 3. So this is equal to x minus 2 plus 3 over x plus 2. So what happens as x goes to infinity? What happens to this term right here as x goes to infinity? It goes to 0. And so this line, that blue line, can you guys in the back see this blue line? They're like, what? Yes? He says no. I saw some guy shake his head no. So I'll make it a little darker. Can you see it now? Oh, awesome. Okay, so this is going to be x minus 2. That's the slant asymptote. What's the trick for finding the slant asymptote? Long division. You do long division, and then you take the remainder, put it over the denominator, and then you kill this. All right. Are we pretty good with limits at infinity? Look over the textbook. Talk to your TA. We're going to move on to the next section, and it is 2.6, continuity. What's it mean for a function to be continuous? What? Has no holes. It has no jumps either, right? Has no holes, has no jumps. It does not oscillate wildly, or at least not too wildly. The typical answer is it means you can draw it with your pencil without picking up your pencil. That's not exactly correct. And now that we have our idea of limits, we can define it a more correct way. Continuity. F is continuous at A if the limit as x goes to A if you can just plug in the value to get the limit. That's what it means to be continuous. So, let's do this problem. So we have a function f of x. You don't know its formula, but you can evaluate it. Is it continuous or discontinuous at x equals minus 1? How do we figure this out? What should we do? Plug in negative 1, is that what you said? Yeah, let's do that. So we plug in negative 1, and we get minus 0.073. Is that right? Minus 0.073 stuff. F of minus 1 is equal to 0.703 repeating. Good. 703. See, I have trouble with those numbers. Okay, so it's negative. More trouble with the numbers. All right, so now what do we do? So we plugged in minus 1. We got this out. What should we do now? Plug in another number. What other number should we plug in? What? 0. Okay, I plug in 0. Okay, and I get this number out. What's that tell us? It's positive there. What else should we plug in to figure out this function is continuous? What? Something close to minus 1. So give me an example. Minus 0.9. Minus 0.9. Oh, minus 0.9 is 1.2222, right? Is that close to our answer there? No, let's go ahead and put in some more 9s. Are we approaching? Oh! Wait a second. I wonder. Do you see what's going on there? What do you think is going on there? It's discontinuous right there. Right there, the computer can't tell that number isn't 1. Minus 1. Okay, so we would say discontinuous. Let's check from the other side. What's the other side say? Minus 0.11. So what happens to this limit? Let's see. That's minus 0.62, right? Minus 0.999. So what's the answer? Is it continuous, discontinuous because the limit's not equal to negative 1? Or discontinuous because the limit does not exist? The limit does not exist. You come from both sides, and you got different answers. Do you guys know what I'm talking about? I can't tell. Yep. Let's see if we're right. Let's hope we're right. Yes! Okay, and we can actually see the solution here, and we can see what happens. And they'll walk you through it. Okay. Let's try another problem. Well, this looks like the same problem. What should we do now? Plug in minus 1. Okay, so what do we get from minus 1? Oh, we got minus 1 this time. That's much nicer. Okay? And then what do? I plug in a number close to minus 1. 001. Oh, look at that. That one looks good, right? And so what do we have to do now? Other side. Minus 0.9999. Oh, crap. Okay. So this one is, this is also, what's the answer? Because the limit does not exist. Oh, yes, we got it right. Okay, so you might say, well, these problems are easy. Yes. But what it tells you to do is it tells you what you have to do to check this. You got to check from the left. You got to check from the right. You have to check at the point. You must make sure that all those are the same answer. All right. Make sense? I want to try a different exercise. I want to try the most the most common problem. This is it. Choose a value of k that makes the following function continuous at x equals minus 7. So kx minus 7 when x is less than 5, 7x plus k when x is greater than 5. How do we do this problem? Yeah. Oh, that's great. He says set these guys equal to each other and then solve for k, right? And what should x be? 5. That's exactly right. So it's going to be k times 5 minus 7 is equal to 7 times 5 plus k. Is that right? Let's make the k's the same, Bart. Does that look good? All right, so 7 times 5 is 35, so that's going to be k times 5 minus k is equal to 35 plus 7. 4k is equal to, what's 35 plus 7? 42. Okay, so k is equal to, what's 42 over 4? What? 10.5. Let's see if that's right. Let's hope it's right, because that sounds good to me. 10.5. Yes! Okay. Every time you do, if you guys sign up for this and start working, every time you get a problem right, you should say yes like that. You should do it in a public place. Yes. And not because it's so much fun. What I'm trying to do is I'm trying to train you, so it's like, yes, that's awesome. Even if it's not, you just do that, and you'll feel like it's awesome eventually. Okay? All right, so what questions do you guys have about this sort of question? Yeah. He says, does a greater than or greater than or equal to make a difference? In this problem, no. But the reason they did that is so that the function would be defined for all real numbers. All right. Let's do one more. Let's see if we can get a different one. It's too different. Here we go. What are values of c and k if f is continuous for all x greater than or equal to 0? Does this problem make sense? How do we do this one? What's C? What's C? Let's start off with C. What is C? C is a number greater than 0. And he says he knows it's greater than 0 because, well, how do you know it's greater than 0? Oh, okay, great. The problem, by the way, in case you can't see it, is x minus 81 all over square root of x minus 9. And then we can define it to be k otherwise. And this is if x is not equal to c. This is if x is equal to c. So what's c? What is c? It's a constant? I know. What number is c? What number does c have to be? 81. Why does it have to be 81? If x is equal to 81, then the denominator is 0. So c is equal to 81, because that's the point that's bad. All right, and so now, what should k be? 9. And how did you get that? But c is equal to 89, right? What do we need to do here? So c is equal to 80, c is equal to 81. I agree. What do we need to do here? What are we trying to figure out? Somebody remind me. I've forgotten, and I can't turn my head. Okay. And c and k, we're trying to find c and k that make what? The function continuous. And what's it mean for the function to be continuous? What? Yeah, but what did I say it means? You can plug in to get the limit. Now, if I say, can I take the limit as x goes to 81 here? Well, I can't plug in 81, right? But I can certainly say, what's the limit as x goes to 81 of x minus 81 all over square root of x minus 9? What's this equal to? 0? What's the numerator equal to? This is a great problem. I'm loving this. The numerator is equal to 0. The denominator is equal to 0. When they're both equal to 0, you just can't plug in. Now you have to go back and be more careful, right? We've disguised the problem. Oh, what do we do here? What do we do to make this behave? We could factor the numerator and I'm going to fill it in. You're doing a great job. I'm going to say that could be square root of x minus 9 times the square root of x plus 9, right? And that's all over the square root of x minus 9. And now what do? What do? We do what we always do. We cancel. Cancel, cancel. And now we can just plug in. And so this is equal to the limit as x goes to 81 of the square root of x plus 9. And I heard this guy say that the answer is 18, right? And so you can just plug it in. That's equal to square root of 81 plus 9 equal to 9 plus 9 equal to 18. Okay, great. We just did a limit. I forgot. You know, the tape in my brain is a little short. Okay, so I'm a little confused. What are we trying to do again? Find C and K, I know. Why? We want the function to be continuous, which means that we should be able to plug in a value here. Okay, and so what should K be? It should be 18. So C equals 81 and K equals 18. Okay, moment of truth. Yes! Okay, look at this bar here. I have no idea how that bar works. But when it's yellow, it means you're doing better. And when it's green, it means you're doing even better. When it's red, it means you're not doing as good. But you should just ignore it because it's all crazy. Okay. So is this question, is that a hard question, really? It makes you think a little bit, right? You have to think about what's going on here. And if you hadn't seen a question like this before, imagine if you had gone into the exam and we just presented you with this question. Could you do every single step that you needed to solve that problem? I think so. I think everybody's like, nope. I think you could have done every single step, but you might not know exactly what you had to do. That's standard. That's why we're working the problems, to make sure we can understand we're not surprised. We don't want to be surprises. I hope there are no surprises on this exam. All right. Next question, boring. Next, how do I get to the next one? I don't even know. Oh, he's reload. Boring, 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 boring. If you guys think these are hard, you should try them, and you can look through the hints. All right. What time is it? All right. So, on Monday, we're going to talk about continuous functions. While I was waiting to come in here, somebody asked me, do you have a question? We don't have school on Monday. That's right. So thank you. Don't come to class on Monday. On Wednesday, we're going to talk about continuity some more. But wait, don't get up just yet. I have one question for you. What is the point? What's the deal with limits? Why would can somebody give me a real world example of a limit? Well, this guy just said instantaneous velocity, and that's right. Instantaneous velocity is the example that we're looking for. I should have told you guys when we're done. And then the next example we're looking for is something like terminal velocity, wind resistance. All right, we're done.